All right. Good afternoon, everybody. Happy Tuesday. So I guess we're definitely getting towards the end of the semester. So we have really today and Thursday. We have next week Tuesday, and that's really going to be sort of the end of our new material for this class. So Thursday of next week will be obviously Thanksgiving. When we get back, it will be study week. And I guess just to make study week a little bit lighter, I'm probably going to just have our final exam review on that Tuesday after we come back from Thanksgiving. And then the Thursday, I could either cancel or I could do an extra Q&A-ish session for more to go over more stuff if needed. But I really have this gut feeling that it will not be requested really. So most likely we'll have today, this week Thursday, next Tuesday, and then Tuesday after we get back from Thanksgiving will be our final class. That will be just final exam review. So I'm going to. Okay, so I mean, I could definitely do some practice problems as well that entire week. That's not a problem for me, so I can definitely do that. So if that's helpful, I definitely have no problem with that. What day and time will be the finals? So I'll have to check that out. So there's a predetermined final exam, sort of, it's a 2 hour block on that week. So I'll have to double check. Once, I think I'll probably check that out before the final week of the semester. So it is actually listed up. I could probably check it out even today. Even I can probably check it today and upload it or send you guys the info on that. So it's typically just it's predefined. So it'll be either Tuesday or Thursday of that final exam week from 1 to 3. That's what it will be most likely. And of course, I'll give you guys some more time because with the whole scanning the PDFs and uploading it to Canvas might take some extra time. So of course I could, give you a little more time so you don't have to worry about rushing to get it scanned up and get the wrong file scanned and so forth. So either that Tuesday or Thursday of that finals week, 1 to 3, with some extra time with the whole scanning process. It looks like for the first exam, that whole scanning there was no real issue. It looks like it was relatively went pretty smoothly actually. So I'm not gonna. I guess we can probably keep it the same sort of structure for the final exam. So anyway, yeah, I guess for the final week I'll do an exam review and go over practice. I go over some problems again, and I'll spend the whole week doing that, which is definitely not a problem for me. I mean, I'm around obviously, so there's no problem doing that. So okay, so I guess we have our sort of our semester somewhat kind of laid out. So let's go ahead now and sort of recap. So I guess last week we had no live class. So we went over, last week, Tuesday, I went over Dijkstra's algorithms. So the next greedy algorithm will be Kruskal's algorithm, which is probably something that you might have learned in 302. But I guess I can go over that. It is a kind of a known type of problem, I suppose. So let's go ahead and just bring these up over here, and I'll make a new board here for this. Kruskal's algorithm. Let's see. I think I'll probably just actually make it so like grid. Maybe I mean I'll have to draw some graphs anyway. So I think as a grid layout, so I can make it more consistent. So anyway, Kruskal's algorithm. So basically, it's going to be a minimum spanning tree algorithm. So basically, I'll just sort of say it really here. So in 302, I would spend time talking about this in more detail, but a minimum spanning tree. Well, it's basically just a spanning tree. So a spanning tree, I'll write this out over here. So a spanning tree is a subgraph that sort of connects, I guess, connects all nodes in the graph. So it spans the graph. So I guess that's the word. So a spanning tree is a tree that spans the graph. So it connects every single node. But a tree basically is a very minimally connected graph. So a tree with V amount of vertices. Remember, this is the cardinality of V. This is the cardinality of V. So the amount of vertices um, will have V minus 1 edges. So we're going to assume an an undirected graph, we'll assume. So basically, if we have V nodes, we're going to pick V minus 1 edges. So we're going to connect all the nodes together. So this is going to be our spanning tree. And then we want to choose a spanning tree with minimal combined weight. And a spanning tree is not really a shortest path problem. So Dijkstra's with a shortest path algorithm. This is not really a shortest path algorithm. I'll put this here just as just FYI. A minimum spanning tree, a minimum spanning tree is not a shortest path tree. I mean, I suppose if you have for Dijkstra's algorithm, you can create sort of your kind of like your DFS forest. You can make a forest for Dijkstra that has all the paths from that starting node to your nodes in your graph. That's also going to be a tree, and it's not really guaranteed to be a minimum spanning tree. So they are different from each other, two separate concepts. So for Dijkstra's algorithm, you want to find the shortest path from your start node to your other nodes. I mean, a spanning tree, you want to find a subgraph that connects all your nodes with minimum total weight. So consider like Dijkstra's would be almost like a shortest path for routing packets and network, basically. So you want to route different packets around, but you want to find a shortest path or the fastest routing to get your packets across nodes. A spanning tree is more like what you want to do is you have a network and you want to get rid of a few redundant edges because maybe you have to cut back. You can't maintain every single possible line in your network, so you have to remove some lines, but you want to remove them in a way where you have a minimally connected graph, basically, is what you're trying to do. That's sort of the idea for a spanning tree. And the other main thing is a tree has no simple cycles. Now, if we have an undirected graph, obviously that edge is two ways, so a cycle is formed. But I guess for this case, I guess so since we are using an undirected graph, a cycle implies if we only take one direction for each edge and obtain a cycle. So cycle really means that we go back to some node that we were already at, basically. That's what a cycle is. So pretty much, like over here, for example, let's put this here. Let me just draw a nicer graph or draw a nicer shape since I do have this. So this would be an example of a cycle. So even though, let's say we have this graph right here and it's undirected, there's no cycle here, but adding this edge will now cause a cycle. Because, I mean, obviously, even without this edge right there, a cycle is still present because obviously it's an undirected graph. But assuming you only can go one direction, let's say, then obviously there's no way to get back to a node. But if I put this edge over here, if I go one direction, it'll still lead a cycle. A cycle is going to happen because I take one direction only. Well, then, if I take this path, we get a cycle. We only took one direction from these edges, and we still found a cycle. So basically, we can't have a cycle essentially. So for this algorithm, we're going to have to introduce a new data structure, or not really new. It's a data structure you might have already learned. So we're going to have to use this union find data structure, which you might have been exposed to this in CS 302. It's just a way to quickly find cycles in your graph. So depth first search can find a cycle, but depth first search has a linear-ish runtime. This is going to be much faster. So this is kind of nice way just if you just want to kind of while you're running this algorithm, this is a way to very quickly find if a cycle exists in your graph. So basically, this is for a disjoint set. So I think you might have also learned it in this terminology. Disjoint set is what union find structure actually is. So basically, what you're going to do is you have the following two functions. So you have first you're going to have the following. So each node has a leader. And we're going to use the following sort of array. So we're going to use sort of the following. We're going to have, right, just here in red, it'll be leader of u equals, let's say, v. If that's the case, that means u's leader is going to be v. It's like a predecessor, basically, like a predecessor array when you do depth first search, which I don't think I did cover that actually. Different kind of structure, of course, but anyway, you want to store every leader basically for every node. So if leader index u contains v, then v is the leader of u. Okay, and of course, use the array to actually implement this structure, but I'm going to use kind of a more a picture representation to make it simpler to see what's actually going on. But of course, the code would be modifying this leader array. But I'll kind of go over how we can use a more of a picture representation to show this leader array. So we're going to have the following two functions, find and union. So I do a find on u, I have to return u as leader. So we're going to recursively go ahead and say leader of u is an equal find leader u, and then return leader u. Now, this is basically, this portion right here is for path compression. Let me go ahead and just box this in. This is path compression. So the whole point of doing this is the following. So I'm going to go ahead and just draw a picture here for a second. So I'm going to actually just use sort of this picture instead for right now. Let's say we have A, Node B, and Node C. And then we have the following sort of setup. So I'm using this picture to represent this right now. But if you had the array, then what would happen is leader index C would contain B, and leader index B would contain A. So C's leader is B, and B's leader is going to be A. But of course, I'll use this picture to kind of when I trace out Kruskal's algorithm because it does make it a bit easier to visualize what's going on. But I'll go ahead and I'll use this picture representation instead. So if I want to go ahead and do a find on A, it's going to return, obviously, A, because A is the leader of its own sort of group, I guess. If I do a find, B also returns A. If I do a find on C, it returns A, but it goes through multiple levels. So C's leader is B, B's is A, and A's own leader. So A is the leader of C. Not a direct leader, but indirectly A is the leader of this group. So what this green portion, path compression, is going to do is going to update this to have C point directly to A. So if next time I go ahead and do a find C, it'll be a constant operation. This is, again, another amortized type of structure. So you may have to do a lot of work. Let's say if C is very far away from A, through multiple sort of, it has to go through multiple sub-leaders to get to A. It takes a long time, that one time to all the way to find a leader, but next time around, though, it'll be instant. So it takes a lot of time once, but then afterwards, it'll amortize itself later on. So there's another amortized analysis type of a problem. So that's what the find does. Also, I mean, I could even extend this even further. So, I mean, let's do another example. I could even have something like this, an extreme case. So let's go ahead and draw another example here. See, let's have this one, A, B, C, and D. So I may not get any examples that will have this, but this is a possibility. Oops, that's supposed to be a B. Okay. So basically, this is a possibility. This may not come up in my example, but in general, this could happen. So if I do a find on D, what will happen is eventually A is the leader. But along the way, though, it's going to update C's leader to point directly to A. And also it's going to update D's leader to point to A. So every single element along this path, they're all going to compress to one leader. That's what that whole path compression does. So that way, it does a lot of work one time, but afterwards, when I do a find C and a find D, it's going to be a constant operation. So amortization, once again, for the win. I'll just put this a little closer. So, and I'll put this a little closer as well, so it's not just sticking out there. Awkward spot right there. Okay. So that's what find does. So, I mean, nothing too complicated there, I don't think, but that's that. And then for union, so let me just make sure I'm consistent. So, okay, so union, UV. Well, all it's going to do is it's going to basically take the leader of U is now going to be leader V. That's all. Now, of course, what you want to do is the idea is this is going to have to be a bigger sort of family, bigger tribe, basically, bigger house. So to get the best optimal results, you really want sort of the, I guess, the group that V belongs to is a larger group than the group U belongs to. If I say using a bigger group, then you just swap that. So obviously you have to maintain some type of a value that stores each node the size of the group that it belongs in. You have to also do that as well. We're not going to focus too much on that, but we'll magically just have it automatically know which is the bigger group to get optimal results. So always the bigger group will consume the smaller groups, kind of like when we have when they sort of unified Germany. West Germany was the more powerful Germany, so West Germany consumed East Germany. That's sort of the idea. So we always have the more powerful or the larger house consume the smaller one. That's how this is going to work. So just like in the Berlin Wall with the whole unification of Germany, same idea. So, okay, so that's going to be basically in fine. So that's all there is to this. So we're going to use this to basically allow us to know, so we don't want to combine elements together that are in the same family. So we can kind of consider Unifying as Game of Thrones reference, which I used that in 302. That show is still relevant even now, I think. It's still, people still remember that show. It's not that long ago. So the whole idea is you don't want to union two nodes that are in the same family. Because let's face it, we don't want to have another Joffrey appear again and cause all kinds of problems in Seven Kingdoms. And remember from the first season of Game of Thrones, he caused that entire massive war in the whole realm. So basically, we're trying to avoid having any more Joffreys, is the idea with the Kruskal's algorithm. Okay, now that we know how Unifying works, let's go ahead and go over the pseudocode for the algorithm. So we're going to have our pseudocode will be just, I guess I'll call the function, which will be Kruskal. And we're basically passing in, I guess, the graph into this function. And okay. And then we're going to have basically, we're going to, I guess, we're gonna make our set basically of all of our, so we're gonna make set. He has, in the book it uses the word make set. So okay, fine. I'll just explain what that means in a second. So you'll first have our, I guess I'll call this K equals empty. So K is gonna be our set of our edges. And then we're going to have our for loop. So for each vertex v in our graph G, make set v. So I guess this is going to set up our union find structure basically. So sets up the union find structure. So the idea is that every single node will be its own leader, basically. We'll show the example of that in a second. And then, I guess in the book, they use this approach. Actually, in 302, I do it differently, but the book way is actually not wrong. So you're going to sort the edges by weight, of course, in ascending order. And you're going to insert, actually, you don't have to even, I guess you can just have it in sort order like this. You sort them by edge weight. And then for each edge UV in the sorted set of edges, you do a find operation. So if find U does not equal find V, let me just look a little nicer, equal find V, then we're going to basically add this edge into our spanning tree. So some set theory stuff here, which is this is in the book, but basically we're going to add this edge to our spanning tree. So add UV to MST, which MST is short for minimum spanning tree. I might use MST more because it's easier than saying minimum spanning tree every single time. So MST is definitely easier for me because it gets repetitive to say the same thing every single gosh darn time. So then we're going to union U and V. And at the end, K is going to be our set, so I guess we can return K. So basically, you sort of put this over here. This is going to this loop will go up to that far. And then this is going to be in our if statement, these two statements. If. So just to kind of have a pseudocode kind of laid out. So there you go. So K is going to be our set at the end. So that's our pseudocode. I'll go runtime analysis in a little bit, but very similar to Dijkstra's algorithm. So anyway, let's go ahead and work out. Let's do an example graph and just trace out Kruskal's algorithm on this graph. So I'm going to, let's have an example over here. Let's go ahead and create some elements. Let's create our graph. Let's see, how many do we actually have here? I think we have several. So I can create one on the fly. I'll have to use the one. It's actually from the book, but maybe I could just create my own maybe, or maybe I use the book one. Yeah, I'll use the one that's in the book, just that way it's safe, I guess. All right, and then we have that. It's a nice big example, so I guess it does help to do a big example in class. I mean, I know typically in class you have a very small example in class, and then in the homework you have this big example which completely throws you off. I used to always not like that in school. Small example in class, let's multiply 1 times 2, and then for your homework, let's go ahead and do some giant, thing like that, right? So this would be a nice large example. I think that covers everything. I think that's all the nodes I need. Okie dokie. Oh well. We have this, and I think I'm getting there. I think a few more edges, I believe. Yeah, we're almost there. Yeah, but I think that I got everything there. Perfect. So I'm going to go ahead and just label these. This will be A, B, C, D, E, F, G, H, and I. I'm going to go ahead and put the weights here. So I have 4, 8, 11, I guess 8 again, sure. Then we'll have 2, then we'll have 6, 7, 1, 2, 4, 7, 14, 9, and 10. Okay. So for the homework and on the exam, I'm going to make sure that the edges have they're all going to be distinct. There's no duplicate edge weights because this makes it easier for grading the homework and the exam. But for example, here in class, though, it's not a big deal. It doesn't really matter. So anyway, the first thing we do is we do our make, what was it called? Make set. Is that what it was in the pseudocode? Make set. Okay. I'm going to first move this over just a little bit because I want to have some room on the right side. All right. I'm going to zoom out here and do my make set. So we're going to have these edges. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So sorry, 9 nodes. 1, 2, oops. 2, 3, 4, 5, 6, 7. I guess I'll put one over here at the top. Okay. Make set. So we have these elements. This is not going to be part of my graph. This is my unifying structure. I'll put this over here just so we don't darn, A, B, C, D, E, F, G, H. Need one more. Okay, fine. Long setup time. It's a very simple algorithm, a very long setup, unfortunately, for this. Okay. So this is going to be my union find structure. So union find. So this structure to the right. Union find structure right there. So initially, each of these elements will be its own sort of leader, basically. So if we do a find A, it will return A, find B is B, find C is C, and so forth. So each of these is its own individual leader. Okay. So of course, we're going to have to sort our edge weights from smallest to highest. So obviously, if we were to work this out, now we're going to have to pick an edge. So our first smallest edge is going to be GH with a weight of 1, I believe. So we're going to list out these steps one by one. So same as in 302, same exact, same sort of idea. So we look at GH. That's our first edge we look at because that's going to be our first smallest edge. Of course, we do a find on G and a find on H. So looking at our union find structure, find G returns G, find H returns H. So we're going to have G, we're going to have H. So we can see here, they are definitely not equal to each other. So we can go ahead and combine them together. So I'm going to actually draw this out here. So I'm going to put this here in green, that this edge is going to be part of my spanning tree. So we're going to have to sort of add GH to the minimum spanning tree. Yeah, I'm going to put it here in parentheses actually, so it's a little better. So that's our first step. So that was it. So far we have that. And we're going to have to, of course, union G and H together. So they have the same exact size, so it doesn't matter which one we pick. So what's going to happen is G is now the leader of this group. So of course, in our array, we would say leader H equals leader G, which would set leader H equal to G. That's what would happen. But I'm using this representation to make it simpler to kind of visualize this. So that's going to be the result. Okay, so let's do a few more steps because obviously we're not done yet. We have to go through every single possible edge. So our next step is our next edge. Well, looks like we have either CE or HI. I'm going to pick HI just because. So HI is our next one. So always pick the next smallest available sort of edge weights. So because, once again, this is a greedy algorithm, so it picks the next best one, always the next smallest, which in this case, HI is smallest. I'm going to do a find on H and find I. So H, find will be G. G is a leader of H's sort of group. And I's leader will be itself I. So clearly, they're in two separate families. So we can go ahead and we can add them to the spanning tree. So we're going to add HI to the minimum spanning tree. I'm going to a union H and I together. We can go ahead and marry them. So in this case, since H is in the bigger tribe than I, then we're going to have I will be sort of consumed by this bigger family. So yes, the bigger family will always be Lannister. Lannister is more powerful, so it's going to consume the smaller family in Game of Thrones. So that's the idea. So we're going to go ahead and mark that this edge is going to be in our MST. So far we have these two edges. We're not done yet. It's not a spanning tree because it doesn't span the entire graph. So we have to keep on working. So the next smallest edge is going to be C and E. That's our next one with the weight of 2. So let's pick CE next. We're going to look at this. So we're going to first do a find C, oops, and find E. So for find C, so in this situation here, C is the leader of its own family, and so is E. So find C returns C, and find E returns E. So clearly not in the same family. So this will cause no problems. So you can go ahead and marry them without having any chance of a Joffrey happening. So we're going to add CE to our MST, and we're going to, of course, union C and E. Let's do both of these steps right here. I'm going to mark this. This is going to be an edge in my minimum spanning tree. And once again, it doesn't matter which one we pick because we C and E are both size 1. So I'll pick C as the leader of this family. Okay. So now let's continue because we're not done, obviously. So now we're going to pick our next smallest one, which will be CI with the weight of 4. And also have AB as well. I'll pick CI first, just because. So what's going to happen here is for step 4, we're going to choose CI. And we're going to have to do, of course, a find C and find I. And of course, find C returns C, and find I returns G, because C is a leader of this group of C and E, and I's leader is going to be G. So find C returns C, and find I returns G. So once again, not in the same family. So we can, of course, combine them. So we're going to first add CI to the minimum spanning tree, and we're going to go ahead and union CI, these two nodes. Let's go ahead and do both right now. So CI, I'm going to mark this as our spanning tree edge, like that. And now we have these two families. So I is in the bigger family. So we have CE is one group, and we have CHI. So the bigger family consumes a smaller family. So the leader of the smaller family is now going to report to the bigger family's leader. So C was his own leader, but now C. So since we're marrying these two members, C and I, together, the bigger family, which has CHI, will consume the smaller family. So the smaller family's leader is going to now have it point to the bigger family's leader. So we have C and G are two heads of those two houses, and G is the head of a more powerful house. So G is now the head of the combination of these two houses. So G is now the leader of E, C, H, I, and of course G, the leader of all of those elements. So E is not directly pointing to G, but if I were to do a find E, it would compress that path and have E point directly to G. Let's go ahead and continue with this, obviously. So the next step will be, the next smallest one will be AB, our next smallest edge weight. So I'm going to now process AB next. So we're going to look at AB. I'm going to first do a find on A and a find on B. Let's go back up and check what's the leader of A and B. So A's leader is A and B's leader is B. All right, well, that was a very interesting case. So it's A and B, which clearly not the same elements. So we can, of course, add AB to the MST, and we can also union. We can go ahead and marry AB to combine these two and to make a bigger house. So let's go ahead and do both. So AB, I'm going to first mark this edge in my spanning tree, and I'll choose B as the leader. Sorry, A as the leader, my mistake. So A is now the leader of this family of A and B. Okay, so let's look at our next smallest edge. Our next smallest one will be EH, because it has a weight of 6. Let's go ahead and look at EH next. We're going to two-column this at some point. Might be able to. How many more do we have left? 1, 2, 3, 4, 5, 6, 7, 6, 7, 8. Okay, not just yet, I guess. I won't do the entire example. I mean, I guess I could sort of at the end speed this up a little bit. So you do EH next. I think I'll go a little faster because this is kind of getting redundant now. So EH is next. So if you do a find E, so looking at find E, it's going to compress this path. Because right now, so if you do a find E, it returns C, but C's leader is G. So right there, this is actually going to compress this path to have E point directly to G. So right here in this step, I'm going to put this here just so we can look at this. Find E. This is going to actually cause a path compression. So this is going to have a path compression happens right here. So this returns G, I believe. Yes. And then find H is also going to be G. Without path compression, it will be G, which means that they are in fact equal to each other. So we're going to discard EH. So we're not going to actually include it in our spanning tree. So let's go up, look at our picture for a second, our graph. So the problem here is if you were to actually add EH, then we would definitely create a cycle because E goes to C, C goes to I goes to H, and H goes to E. Also at the same time, it's an undirected graph. So this edge is redundant because technically E can reach H. It can, or H can also go to E. They can be reached among each other. So having this extra edge right there is redundant. We're trying to have a minimally connected graph because we're trying to having budget cuts, trying to cut back on this network and remove any edges that we don't really need. So trying to remove it. So in this case, we're going to not include that edge. We don't. That's redundant. Okay, so fine, we got that out of the way. Let's look at our next examples. We have CD next. I'm going to go ahead and go a little faster now so we can get this over with quicker. We can see the pattern, pretty simple. Usually nobody gets this wrong, even in 302. No one gets this question wrong on the exam, really, because it's really an easy item to trace out. So find C gives you C. Find C is going to be G, and find D is going to be D. This will be G. This is going to be D. So they're not equal to each other. So we can go ahead and we can add this edge, add CD to them in a spanning tree. And we're going to go ahead and union CD. Let's go ahead and do this really quick. So CD, we're going to add this into our spanning tree. And C is part of a bigger family, so D will be consumed by the bigger family. So D's leader was itself. Now D's leader is going to be G from this point on. So D, if I do a find D from now on, it returns G. Okay. Let's see what else we have. So our next smallest edge is going to be AG with a weight of 8, the next smallest one. So we're going to, go ahead and put this here actually now. So step, I think it's step 8. I'll kind of two-column this a bit so it's not too it's a little better, I guess. So step 8, we're going to look at AG. And we're going to do a find A and find G. And, well, find A returns A, and find G returns G. So, once again, these are not going to be in the same family, so this will not cause any problems. So we can go ahead and we can add AG the spanning tree, and we're going to combine AG. We're going to union them together. Let's do both right here. So AG, I'm going to add this into my spanning tree. And since A is in a smaller family, because G is in a bigger tribe, then A is going to have to point to G from now on. So now B's leader also will be G from now on as well, but it's not directly. It has to go through a path compression potentially. If we do a find B, it will do a path compression again. So let's go ahead now and look at our next smallest one. Well, happens to be BC is my next smallest element. So BC is next, the next smallest edge weight. So now we're going to look at BC. I'm going to do a find B and find C. So find B will cause a path compression, and it'll update B to point directly to G from now on, because B went to A went to G, so it's going to compress the path from B straight to G. So I'm going to also box this in, that this is going to cause a path compression. So it returns G, which is the leader of B, and C's leader is also going to be G, as we can see from our structure. Look at this. C's leader goes to G, and B also goes to G. So that means this edge is redundant, equal to each other. They're both in the same family. We don't want to have a potential Joffrey to happen. So we're going to discard BC. As we can see here, that technically from B, we can reach C, because B goes to A goes to G, G goes to H goes to I goes to C. So B already can get to C. So this edge is redundant. We don't need this. We're trying to minimize we don't want to have every single edge. So we don't need to have this edge. This can be thrown out. So it's not going to really help us. We already have B and C. They are already connected to each other, so you don't have to worry about that. Okay, so now we have our next smallest one will be DF. So we can see here it's definitely a greedy approach, because always pick the next smallest edge weight. So DF is our next smallest available edge weight. So we're going to have DF for Doug Funny. So find D and find F. So we can see here, F is itself, and D, its leader is going to be G. So D's leader is G, F's leader is itself, F, which means that they are not in the same family, not in the same group, which means that we can combine them. So we're going to go ahead and add DF to the spanning tree, and we're going to union DF. So let's go ahead and put that right here. So we're going to mark this as a spanning tree edge. And since F is in a smaller family, D is in a bigger family, then F is not going to point to this bigger family as well. So I think we're kind of already done now, because everything now points to G. But obviously, it would have to do more work. But of course, if we had a count of how many elements we had in our spanning tree edges, we could probably stop right here. But let's do the last few steps kind of quickly, just for the heck of it. So for 11, our next smallest one would be, looks like, oh, did I make, darn, I made a mistake earlier, actually, because I think EG was our next smallest one. Okay, that's fine. I think after CD, yeah, after BC, sorry, after BC, oh, after CD, oh, darn, okay. That's okay. So step 8, so I'm going to go and move these down a little bit. That's fine. Oh, well. I'm going to try to quickly salvage this if I can. I think it shouldn't make a big impact, though. Hopefully it doesn't make an impact. So this will be our true step 8 right there. It's my mistake on that. So step 8, because step 7, I was looking at CD. After CD, I would have looked at EG would have been next. I think I can still salvage this. So EG would have been next. So we do a find on E and find G, like that. And find E would return, so I think I already passed compress earlier. Okay, awesome. This doesn't really make any difference at all. So find E would return G. And then find G returns G as well. So this would actually be a throwaway. It's okay, so it's not, didn't really cause any massive problems. So discard EG. Awesome. So technically it didn't really end up causing any real problems really for me by messing that up. To make it into a G, not a 6. There we go. So this would get sort of discarded. So my apologies on that. And then I'm going to go ahead and label this as step 9. Oops. If I didn't miss anything, step 9 would be right there. This would in fact be step 10, which is not affected at all. Then step 11 is right there. Awesome. So didn't really cause any problems really. So I guess I got lucky right there. Cool. So for step 12, what's our next? I'm going to zoom out a little bit here, just maybe move this over a bit. Step 12, our next smallest one is going to be IF. Actually, I'm going to say FI. I think F. Yeah, FI. I'm going to say it's alphabetical orders. FI is next. I think you only have 2 more to do, or 3 more. Okay, awesome. Almost done with this. Perfect. So FI is next. We do a find F. Find I. Go up here really quick. I and F both point to that same element. They both point to that same sort of try, because find F returns G and find I returns G as well. They both return G, so it's going to essentially it's going to discard this edge. I think there's 2 more steps left. Okay, good. Almost done. So Fi, we discard that. And then we have BG is next, the next smallest one. I think I'm going to go ahead and sort of do this really quickly, because BG, they both have G, I believe, as their leader. So I can just sort of make this a little bit quicker. They're both going to be G. So they are in the same family. So we cannot combine these. We're just going to go ahead and just discard BG, because this is actually already in the same family. And our last edge will be DI, or yeah, DI. That's going to also, I think they're both in the same family as well. So step 14. So almost the last one. DI. You find D. Find I. They both return G. So discard DI. So of course, if I look at D and I, you can see here that find D returns G and find I returns G. So D's leader will be G and so is I's leader. They're both G. So they're both in the same family. Discard it. And every edge has now been looked at. So of course, it could have finished it earlier, which it did. So if you had a way to count, it had like a counter that sort of kept track of how many, try to sort of squeeze them together a little bit, squeeze these because it's a little bit further apart. So if you had like a counter, you knew if you already inserted v-1 edges into your spanning tree, then at that point you already know you can sort of stop But of course, in the worst case, you have to go through every possible edge until you can finally be sure that you hit the every single possible edge. So I'm going to go ahead and just zoom back in now. Just want to put those together just so they're not too spaced out. So really, for homework or for an exam, you have to kind of show this. Now, once again, the problem is union fine structure can be a little different for everybody because, for example, when we had, let's say we first looked at G and H, I could have had H as the leader instead of G. So there's a chance there's more than one possible solution. So one trick is to not really verify union fine structure or make the rule where the bigger family will consume the smaller family, and also make the rule if there's a tie, then the leader is going to be whichever node is earlier in the alphabet. So for example, if I had find A and find B, and they're two separate families, and they both have the same size, because they initially, at the very beginning, A and B were both size 1 houses. And you want to combine them, and since they're the same size, then A is before B in the alphabet, so A becomes the leader. That's another way to kind of help break that sort of tie. So maybe for the homework and for exam, the rule is going to be always have the bigger family will consume the smaller family. If they're same size families, then pick the one with the leader who has a earlier alphabetical order. So A was earlier in alphabet, so was G for G and H. So I'll probably make that clear on homework and on the exams. That way it becomes more deterministic in terms of grading it. So anyway, but that's sort of the steps you want to show for this on a homework or the exam. Nothing really too hard, really. So I'll post these notes obviously up on Canvas. So anyway, let's go ahead now and go over runtime analysis and then go over sort of the proof, or at least a vigorous hand wave proof that shows that this in fact is going to work. So let's go ahead and set this up. Typically for these greedy algorithm proofs are always a little bit interesting. They're always going to be some type of a proof by contradiction, basically. The idea is that if it was a better solution, it would have found it earlier. It's always like something along those lines, usually. Anyway, so let's go ahead and write this out. So runtime analysis. So the simplest way is we first have to sort. We sort all the edges. Now, here's an interesting concept. So, I mean, I guess for now, we'll say that if you use a comparison-based sorting, it's going to really take O of E log E time to sort this. Because you can't do better than N log N for sorting. So we'll go ahead and just not use radix sort for right now, because once again, we don't know. Maybe the edge weights will be so large, the radix sort won't be able to be used really. So the idea is that if, let's say, our edge weights are kind of small in size, we could probably use radix sort actually to sort this to get it in O of E time. But for now, we'll just kind of keep it like this because we can't really know for sure how big the edge weights are going to, how big numbers size-wise are going to be. So we'll assume they're very big in size where radix sort will not really work well anymore. So we'll go ahead and assume we'll use some comparison-based sorting. So quick sort or heap sort or something to get O of E log E. And we can rewrite this actually because E in the worst case, so E at most would be really V squared. So I could replace E with V squared inside this logarithm, and I could rewrite this to really just be the following. So I could say, well, E log V squared, I can set this as 2 E log V. So I could actually have it as O of E log V to actually sort the edges by weight. So here's going to be the runtime, actually, the true runtime to sort by, oops, weights. So it's going to be our actual runtime for that. Awesome. And then we have to essentially sort of go through. So we have to iterate through each edge. And then we're going to do a find and a union. So union is going to take O of 1 time because it's very quick. We just combine two elements together. So it's a constant operation. Now find is not always going to be constant because sometimes you have to do path compression. So most of the time, find will be constant, but sometimes it won't be. And turns out, if you do this, so this is going to run e number of times. Let's go ahead and put this here. So runs e times. So the combined total, so find, it's going to be a combined total of O of, I guess, log V, I suppose, because you also have V elements at most, O of log V. But we can amortize this. So the complete total of work that we're going to do an entire lifetime at a whole span of this algorithm will be log of V. So we use E number of times. If we average it out, it's going to average out. So it's going to basically amortize to O of 1. Because we're doing less than, so if you take all the complete summation, the complete work we're going to do will be O of log V, and we average it E times. If we average this out, if you amortize it, it's going to be O of 1. So this loop will take O of E times. So you first sort by edge weight plus this loop that's going to start adding elements to our spanning tree. So overall runtime will be O of E log V. So overall runtime is going to be O of E, the cardinality of E, log V. I'll box this in as well. So that runtime, that sorting is actually a bottleneck. Now, of course, if you have very small, if our size of our numbers for edge weights were small, we actually could sort this using radix sort actually, and then get an O of E runtime actually for Kruskals. But that's only if we can have the assumption that the sizes will be relatively small for the edge weights. The radix sort will be much faster than quick sort or heap sort or whatnot. So basically the proof that this is going to work. So the idea, well, this is actually really far-fetched kind of proof. The idea really is that you assume it doesn't work. If it doesn't work, then a contradiction happens. So you assume that basically Kruskals does not work. If it doesn't work, then you'd have to replace that edge with a smaller size, which that would be a smaller spanning tree than the previous one, which is a contradiction. So it's sometimes proofs are kind of hard to explain, but really that's all there is to it. So you prove that it doesn't work, that this is not going to give us the best algorithm. And then if that's the case, well, the contradiction is that it would have chosen the smaller edge weight earlier, because a greedy approach, it picks the next best one every single time. So if, let's say, so I mean, I guess I can sort of go over a proof on this. This is not a very scientific proof, but I don't want to go too in depth with this. Let's say we have the following sort of elements right here. Let's say we have, it's going to be our graph and our spanning tree. Let's say that the minimum spanning tree actually would be these edges right there. Right, that's our solution. Let's say for right now, for some reason, Kruskal's algorithm happened to choose this instead, which is not going to be our minimum spanning tree. Then it's a contradiction because as we're picking our next smallest edge, so let's say, for example, the ones in green are my two smaller ones. Well, Kruskal's would have chosen these two before it would have chosen that last one. So there's no way that edge could have been added before that other edge right there. That's the proof really for it. So if that was smaller, it would have been chosen first. It would have been added first before the other one could have been added. And this one can't be added because this would actually cause a cycle in this undirected graph, undirected tree, whatever you want to call it. So that's the proof for this. So I'm not going to really test you on the proof, but that's the proof for this as to why it works. So a negative edge would also work for this because it's not going to add pathways. It just picks the smallest one every single time. So it picks the smallest one, and then it will try to add it to our spanning tree, making it greedy. And because that greedy approach, that's why it works, because there's no way it could have gotten a larger result because it always picks the smallest edges first. So there's no way an edge that was larger could have been picked first and added before a smaller one could have been picked and added to the spanning tree. So that's why this actually does work. So that's kind of our last sort of greedy algorithm. So I went over Dijkstra's, Kruskal's, and Huffman coding, which are three main or three basic greedy algorithms. So next time and next Tuesday, I will begin covering dynamic programming algorithms, which are pretty nifty. So a few of them will cover graphs, and other ones will cover just some basic topics just to give us an idea of how to think of a problem or how to understand the way it works. So I'll cover dynamic programming, kind of just talking about it. Then I'll do a couple of known problems, and I'll go over probably graph type problems next week on dynamic programming. So I'm going to cover next week will be Bellman Ford and maybe the other. I think Bellman Ford and Floyd Warshall are two main. I think those are two graph theory problems that involve dynamic programming. Next time I'll cover. I'm going to try to cover this chain multiplication in matrices and either knapsack or just kind of change breaking problem. But anyway, that'll be kind of our sort of next two lectures. I guess that'll be it for today. So I guess stay safe. Thanks for watching. Take care, you guys. And I will see you guys on Thursday. Yep, thank you. Take care.